My name is Silvia Ray Gomez, and today's webinar is going to be on pipeline modeling. Can forecasted results be trusted? This isn't exactly a new topic, and the reason I am bringing it up again is because often you tend to hear people say that they don't do pipeline modeling, and this is on the basis that forecasted production usually does not match the actual production, and that leads me to talk about some of the important aspects of building a reliable pipeline model and the considerations that will allow us to minimize the error associated with generating production forecasting. To generate a reliable forecast, we're going to think about 5 main components. The surface calibration, and this is when we're considering how additional system losses are going to change as we change the system pressure and the rate. Then we have the compressor calibration, where we are going to ensure that the capacity curves are going to be representative of the machine capability. We also have the deliverability or inflow selection, which is going to represent the change in inflow capability over time, and also the Wellbore model or the Wellbore calibration, that this will effectively model the current pressure loss effect, but is also going to predict when we're going to have liquid loading and when this might be causing an issue. And lastly, when we bring all of these components together, we're going to validate today's conditions and also the future conditions. So this presentation is going to focus on these 5 main components, but just keep in mind that this is going to be a short presentation, so I'm just going to be hitting all of the main points that you might want to review so that you can actually come up with a reliable production forecast. So when we are developing a pipeline model, there are really 2 main objectives. One is to create something that reflects true operating conditions, which is relatively easy because, as you know, you can tweak any operating parameters and get that match. The difficult aspect here is going to make sure that all of those tweaks are going to be representative and are going to reflect your changing operating conditions. In order to construct that model, so this is going to reflect the changing conditions, we need to make sure that we understand what's happening in the gathering system today. Some of the past accessible ways of modeling didn't really allow for users to produce some of the best results, and this was because making simple adjustments to the measured pressure in the model didn't actually match up with the future results. Unfortunately, modelers will tend to adjust those correlations by using either the pipeline roughness or just do some correlation adjustments or just focus on adjusting the flow efficiency. But all of these parameters actually do is just adjusting the frictional pressure loss components, and in situations where you have a restriction, it will work sufficiently because with small changes in rates, you will see that there is an appropriate adjustment in your pressure loss components. However, in situations in which we have liquids that are going to be gathering in low spots due to low gas velocities, what we could see is that it wouldn't reflect the changing conditions adequately, because with the hydrostatic pressure loss or with liquids sitting in those low spots, it's not going to adjust a whole lot. You're not going to have the same additional pressure drop when you're going to be increasing your flow rate. And this is evident when reviewing these plots, because you can actually see that if we focus in low velocities, the friction loss is negligible, and fudging a match just by adjusting the correlation or flow efficiency will not account for future conditions appropriately. As you can see on the plot, with small increases in rate, a large increase in pressure is going to occur. And this is not the case with liquids gathering in low spot. If anything, the pressure loss is going to remain the same, or that loss is going to reduce, because you're not going to be effectively able to reduce those liquids through the line. So this is where this process hinges to be. What we will end up finding is that the process will not be suitable in all cases. So what is important is to go back and look at the root cause and see how these adjustments are actually going to be affecting us in the future. Where we always recommend starting with is understanding the data that we're going to be using for calibration. It is very important to start with the stabilized rates and pressure data. We want to minimize any transient pipeline effects within that data, because all of our correlations are going to be based on steady state conditions, meaning that the rate that we're going to have coming in will match the rate that we're going to have coming out of that system. So always try to have a look at your data and find the most stable operating period possible. The graph that we see here is going to show the gas rate to the main delivery point over time. And so that allows us to very quickly pick a point in time that seems to be stable. For example, this point here in the middle. In here, we can actually see 4 days of production time, and we can see that the rate is very stable in here. Then, we can actually look a little bit closer and get a feel for how reliable the production data that we have on this particular well level is going to be. So we're going to review the production data and ask the question, and if this actually means that we actually need to go back to the operators and determine some of these things, definitely do so. We want to determine where the pressure measurements are made, identify whether or not they are going to be made at the wellhead or after all the separation equipment on that individual facility. This is going to make a big difference when we're going to be looking at the data, and we're going to be looking at the model and comparing measured versus calculated pressure. And this is going to allow us to factor in where we're going to have any additional pressure losses in the field versus the model that we're going to be building. We also want to get a feel for the reliability of the data. How is this data being measured, or how is it being recorded? So we want to ask a couple of questions. Are we getting that data electronically? Is it going to be recorded on a frequent basis? Or if it's in frequent production recording, are the operator going once a week, and are they able to get those pressures recorded and entering them into our data system? All of these questions are going to allow us to look closely on how we can actually calibrate within that particular system. If we're looking at our rate history for individual wells, as it is shown in red in this plot, and is purely a stable rate, but also if we actually start seeing a little bit of fluctuation in blue in our pressure data, and if this fluctuation is going to be around, let's say, 150 kPa or 20 psi, we know that we cannot calibrate our system any closer than that. So once we determine and look at the data, we can enter the data of our model, and we can enter that for comparison of the measured versus the calculated results. It's always important, once you enter the data into the model, that you limit the variables, so you can really determine where the difference is between the model and what's happening in the field. So things that we're going to do, we're going to enter what we know. So for example, if you know the well rates, then we're going to be entering this information as fixed well rates. Also, we can enter our pressure. So if we have the delivery point pressure or your suction pressures, or for example your inlet facility pressures, we can enter all of these as fixed pressures. All this so you can actually then focus on what's happening in the pipeline segments. We can always recommend starting with what you know. So once you generate that model, you're going to make sure you verify what's coming into those facilities. You're going to verify the suction pressures and inlet rates, and this is going to be setting the stage for using the data diagnostics. It is really important when we're comparing our measured and calculated pressures, and especially when we are in larger fields, to look at the overall trends. The different data signatures that I'm going to be showing you today are going to help you hone in on what's happening in that field and what you might be missing in your model. The next few slides that I'm going to show you are maps that we generated in the IHS Piper software. The bubble map here is showing the difference between pipeline measured pressures and calculated results. The tolerance limit that we set was plus or minus 10 psi and is going to be shown in yellow. The gas is going to flow from the compressor station, which is here on the right. Everything to the west of that compressor station is upstream. So looking upstream, I can see that everything is calibrating really nice, and until I get to the northwest section, where I can see that there is a change in colors, all of these wells in this northwest section are out by a common amount, and that common amount is in the range of 10 to 20 psi higher than what we're actually calculating. What this data signature is going to show me is that there is a point in my model where there is a pressure loss that I'm not accounting for, and I actually need to know more information about this. So now, if I actually take a closer look and verify that true difference, if I start looking at the annotations, I'm showing a difference between the measure and the calculated pressure. So looking from the south to the north, I can see that the different ranges from 17 to 22 psi difference. I can also view the locations that I don't know any information about. And I can see the last yellow well, which is within plus or minus 10 psi. There is also a portion of line segment where I have no measurements, and then my next well, which is outside the acceptable range by about 17 psi. So now I will just focus on the area and gather more pressure information to pinpoint the source of that additional pressure loss. So when we are reviewing these data signatures and we see a step change, the step change means that there is a localized difference in my model versus what I'm seeing in reality. And this difference is going to allow us to ask more questions. So as I was mentioning before, we get operators to go out and take a few more measurements and confirm that this is actually not related to any kind of losses at surface facilities. If we isolated that additional loss within a pipeline segment, then let's figure out why. We can look at the velocity within the pipeline and see if we have a very low velocity. So if the velocity is low, that will be likely an hydrostatically dominated effect. And we look for an elevation change in the system and evaluate the potential of liquid loading or liquid accumulation in those low spots. If it is a very high velocity, then we're going to start looking at everything that could affect the frictional pressure loss component. You always look at your data. That is a common weak point. It's possible that we actually have a different pipeline diameter or a different pipeline length compared to what we originally entered from our database. The next step, if we actually rule out that it's a data issue, we're going to be looking at the operational parameters. We can check if this is actually due to wax or a scale buildup, or if there is some sort of unknown restriction such as a hot tap. Unfortunately, sometimes the hot tap borehole is smaller than the connecting lines, and this can actually cause a restriction. So we need to look for any possible item that can actually be causing that frictional restriction. In the case that we actually have determined that it's not going to be a data issue and this cannot be changed in the model, we need to account for those additional losses accordingly. For example, for frictional losses due to a hot tap, we know that we're not going to be able to remove that loss from our system. So we want to make sure that we consider it under changing conditions. For example, if we're drilling new wells or anticipating any additional gas inflow, we would expect that type of loss to increase. So we will model it as a variable loss. In the case of liquid sitting in a low spot, we want to evaluate whether or not it's going to be valid to keep that loss in our model and keep it in as a fixed type loss. Are we able to really pick that line and remove those liquids by picking? If not, we could leave that in our model, but we need to keep in mind under bringing in additional gas that we want to remove that loss. So the first data signature is that step change that is going to show us that localized difference in our model versus reality, and as I mentioned before, is going to suggest us to ask more questions about it. Now, the second common signature that we're going to see is a systemic differences within the system. As we look from our compressor station out into the field, what you would see is the difference between the measure and the calculated pressure is getting larger and larger. And this is a very good visual tool, and you can see this by the changes between yellow and actually getting into any kind of hotter colors. In this case, just getting into the red colors. So this signature can point to what you could be missing in your model. That's why one of the items I mentioned at the beginning is to check your inlet rate versus your model rate and make sure that they are representative of one another, because if they are not, you could see that systemic difference within the model. So if you have been able to rule that out, start looking at multi-phase flow effects and make sure that you're actually accounting for those. Make sure that you're using the right multi-phase pressure loss correlation, and make sure that you actually incorporate the elevation changes and the appropriate fluid properties. As you can see, diagnostics and the surface calibration can actually tell us way more about how our system is operating and how it may operate in the future. It is about truly understanding what's happening in that system and how that system is going to respond to changing conditions. As model errors can creep in due to human errors such as data entry, we really need to rely on these signatures and ask more questions to why our model is actually looking different. We want to focus on ruling out any of those issues, and when we hone in into an additional pressure loss and have been able to attribute it either to a hydrostatic or a frictional pipe restriction, then we're actually going to be able to model it appropriately, and we're going to make sure that this is going to be representative of our changing conditions. So in summary, the best practices for the pipeline calibration portion is to make sure that we start with a data set and understand the limitations of that data set. We're going to make sure we know where those pressure measurements are made and how close we can actually calibrate our model. Then we can actually move into the diagnostics, and we're going to start with what we know. We're going to verify that the model rate and those of the main facilities are going to be the same. All often, people tend to forget to put in items such as third-party gas or a third-party well, so make sure you are accounting for that data too. You're going to start with the main facility and work your way out. We're going to look for the data signatures. We're going to look if it's a step change or a systemic type differences. Those types of informations are going to further allow you to figure out what you're going to be missing in your model and where there is that disjoint. And then lastly, prior to making any adjustments to your model, we're going to make sure that you validate it and that you confirm that if you have any kind of additional losses, you're going to confirm how to treat it. The surface calibration is only going to be the first step and perhaps one of the longest portion of this presentation. Unfortunately, many people make the common mistake of trying to overmatch the system where they don't really understand the data. So this is what I try to focus on this strongly today. Then our next step is going to change a model into forecast mode and to make sure you're accounting for changing conditions. For this, we actually want to include three components: deliverability, or our inflow model, and this in conjunction with the reserves, so we can actually account for that change in reservoir pressure that is actually happening with depletion. We also want to model the compressor capacity. So modeling all of these things are actually going to allow us to keep our model within a reasonable range and within reasonable limits of what the field is actually capable of producing. So with the compressors, we need to understand the capability of the unit and make sure that the compressor capacity curves that we're actually going to use are going to be representative of the range the compressor can operate. One of the first steps in doing this is to plot our current operating point on the compressor capacity curve. So the plot I'm showing on this slide is an aerial compressor performance curve, and this was generated in the aerial performance software. And shown on this top portion of the graph is the brake horsepower versus the suction pressure, and the bottom portion is going to be showing the corresponding flow rates versus the suction pressure. The red dot is going to indicate my current operating point. If I plot it on the curve and it doesn't match, I need to investigate the reasons why this is not matching. The chart that I'm showing on this slide is an extract from the IHS Piper course and is showing a checklist that we will need to go through in order to validate our compressor curve. There are going to be lots of reasons why the operative point might not be landing on the curve. We can actually have systems that are dynamic and they keep changing over the course of life of the field. And also another option is that the compressors can actually be moved to other locations, or the cylinders can be replaced. So if we receive this compressor capacity curve, we want to make sure that this is representative of the compressor that is out there in the field. Also, there are other parameters that can change. Operative conditions can change. We can actually have different rotating speed, or maybe the gas analysis is going to be different compared to when the curves were initially generated. So we need to confirm those kind of items as well as the operational items. It is also very common to have different variable volume pocket settings or different clearance settings on a reciprocating type machine, or also a change in a sliding valve position on a screw unit. So going through this exercise is going to allow us to effectively match our suction pressure and our flowing capabilities to our field. It will also allow us to verify how much capacity we're going to have in that unit. So when we move to development mode, and if we think about, for example, adding more wells, we can actually understand how much more capacity is actually going to be remaining into that compressor. After we have added the compressor capacity curves to our model, we also need to make sure that we are going to be accounting for the reservoir pressure changes as the reservoir depletes, but also the reservoir inflow response with changing surface and bottom hole pressures. we want to make sure that we select the right reservoir model. And if we think about conventional type systems, the Rollins-Shiller back pressure equation is the one that we tend to use. But in systems where we have unconventional or very low permeability systems, we need to make sure that we are accounting for the transitions between the transient and boundary dominated flow. Another option is if we have cold bed methane wells, we need to make sure that we're going to be accounting for other factors such as the absorbed gas contribution. So just making sure that we, depending on the type of system we have, that we use the right correlation. The plot that I'm showing here is showing the gas rate versus time, and the difference between these two models can be quite significant. The red line is using the conventional type model, and the orange line is a transient model. If the models start at the same rate and utilize the same total reservoir volume, you can see the depletion is very different using an IPR curve versus a horizontal multifrag model. So it could actually be quite significant, the difference between one model and another. So once we have those types of items, before doing the forecast and validation, you also want to include the wellbore component and make sure you are accounting for frictional and hydrostatic effects through the wellbore. The plot that we see here shows the pressure versus gas rate. The black line indicates the inflow capability at bottom hole conditions, and the pink line indicates the wellhead operating conditions. If we actually draw a vertical line from that black line down to the pink line, it's going to indicate the total frictional and hydrostatic pressure losses within the wellbore. And the benefit of this curve is that it shows it over multiple operating conditions as opposed to tubing performance curves. It also shows us whether or not we are frictionally restricted as well. If I brought your attention to the bottom of the graph on the zero pressure line, and then we move to the right, the theoretical maximum operating condition at wellhead is going to be about 1.15 million standard cubic feet per day, while the bottom hole is 1.36 million standard cubic feet per day. This indicates that we're going to have a very small restriction to the wellbore. The other benefit of this plot is that we can identify at what rates liquid loading may be an issue. We can identify where the blue line crosses with the black one, and this is the critical liquid lift rate at the end of the tubing. To effectively model a system, we need to consider the frictional and hydrostatic losses that we're going to have to that wellbore, as this could be the bottleneck in the system, and we can actually have an effect on the future operating conditions. So once the models have been incorporated and the production forecast has been generated, the results can actually be verified by comparing the historical rates and pressures to the forecasted ones. The plot here shows a common trend between historical and forecasted conditions and confirms that the IHS Piper model that we use is representative of actual operating conditions. The ability to view the flowing rates and pressures is going to provide a quick diagnosis of why the trends do not match. Once we have these components into our model, we can do that base case validation, and this is a very important part of wrapping everything up and tidying everything together. On the primary y-axis, the plot shows gas rate versus time and liquid rate versus time. And on the secondary y-axis, there is pressure versus time. We have the gas rate represented in red, the total liquid rate is going to be represented in purple, and the bottom hole flowing pressure is going to be represented in black. So under baseline scenarios, where we are not going to be adding any additional wells to the system, or there is no change to current operating conditions in any way, we want to see the forecast extrapolate out and follow the same historical decline trend. This extrapolation is going to allow us to confirm how reasonable our reservoir model is. If for some reason our forecasted trend tends to die off quicker, then history is going to suggest that we want to look back at our original reservoir model and determine why the model is under-predicting the total reservoir volume. The other components of this plot, such as the bottom hole flowing pressure and the liquid rate, are going to allow us to make sure that we are forecasting in alignment with historical trends. It also allows us to further hone in other operational components within the model and confirm that they are behaving as anticipated. For example, if we started forecasting this model and see that there is an increase in the gas rate, but we could review the historical bottom hole flowing pressure and the wellhead pressure. If forecasting at surface at the same historical pressure, but the pressure is way lower at bottom hole conditions, then we know that we are not adequately modeling what is actually occurring on the wellbore. So as you can see, going through this validation is going to help us feel a little bit more confident with what we will get in our forecast results, and we're going to be allowed with this just to go into that predictive mode. The next few slides are diagnostic maps from the IHS Piper software. This is the frictional pressure loss map, and if we look at the legend, we can see anything below 5 psi per mile is going to be shown in purple, and we can go up in 5 psi increments to a pressure of 35 psi per mile or higher, which is shown in the red color. In this model, the cooler colors represent low restriction and pipeline capacity, while the warmer colors are going to indicate a potential restriction. So these type of plots are a good visual way of identifying where we have any potential restrictions. But the real power is putting this together with your reservoir model. So just looking at this model, we might think that there are a lot of restrictions. However, tying this with the reservoir capacity may tell us a very different story. This is the well uplift map, and it shows the difference between our absolute open flow conditions at this point in time and our current operating rate. So right away, we can pinpoint where there is remaining potential. The light color wells indicate there is less than 0.25 million standard cubic feet remaining between the absolute open flow and current operating conditions. As the color range gets a little bit warmer, the range increases by 0.25 million standard cubic feet. Very quickly, we can identify on one of the lines in the northeast where we have at least 3 wells with potential, 2 of which have a potential on the range between 0.25 and 0.5 million, and one in which we have a potential of greater than 1.75 million. This map is going to allow us to focus on the regions that have the most potential, and then we can look back at potential optimization scenarios, such as whether or not it is better to look at the line looping or compression, or if it's better to add pipeline and compression capacity. The next plot that I'm going to show you is a plot that combines all of the reservoir inflow models at one point in time. And the curve is the summation of the inflow at a certain node or at a certain junction within the system. So in here, we are plotting pressure versus rate. The red curve indicates the current inflow capability when operating at a given pressure at that point in the system. And this takes into account all frictional and hydrostatic losses upstream of this location. And the green curve is going to show us if we were to remove all of the frictional losses within that line, that is the rate we could produce. This curve allows us to quickly evaluate and determine if whether or not adding additional pipeline or compression capacity will actually improve production. So in summary, there are really 5 main components that help us to produce a reliable pipeline model. We're going to start with the surface calibration and make sure that any additional losses within the system will reflect changing conditions. We're going to make sure, when moving to forecast mode, to model only within the applicable ranges of the field. Also, we need to make sure that the compressor performance curve is representative of those units that are going to be out in the field. We need to make sure that the deliverability model or an inflow model is going to perform the same way, and of course taking into account all velocities within the wellbore. The only way to really wrap this up is making sure that you go through all of those forecast validation techniques and make sure that your historical production lines up with your extrapolated forecast results. So now, finishing this presentation, let's just look at some of the questions. I know that we're a little bit short of time, but I'm going to make sure I answer some of the questions that we actually have from the people that attended this presentation. So one of the questions is asking me, which multi-phase flow correlation would you suggest using? I'd probably say it completely depends on which correlation you're thinking about. So if we talk about the IHS Piper software, we have different types of correlations. So in the software, I know that we have the mechanistic model that is called Petalas and Assis, but we also have the Flanagan correlation as well as the modified Bex and Brill's correlation. When using the correlations, make sure that you're using different correlations within the developed region. For example, if we think about Becks and Brills, this one was developed on a test situation, flowing air and water through a unit. So let's say if we have a gas-water type situation, we can use this correlation on that range. Or for example, if you have a mechanistic model, or petalaz and assist, this one is actually a very detailed relation that covers all parameters such as pipeline inclination, flow regime. So it's a really good correlation to use, as it should cover a much larger range of situations. Okay, let's check other questions. How to differentiate between hydrostatic and frictional pressure loss. So these are two different components. So the frictional loss component is dominated by the velocity square, while the hydrostatic is going to be dominated by the height change and the density on the fluid. So when there is an additional pressure loss that we're not considering, we actually hone in, and if it's quite low, then it might be actually a hydrostatic case. It might not be frictional on this particular case. How to forecast once liquid loading occurs? That's a really good question. So once liquid loading occurs, there are going to be certain assumptions that we can actually make. As you may well know, in some cases it may actually load up very quickly, or we're not really sure at what rate it will actually load up. So when we are doing any forecasting, we have a couple of different options within the forecasting. You can either identify that it's liquid loaded and choose to shut that model, or send it to apply different methods. So in the case that maybe we were to add a plunger lift, we look at trends, areas decline reduces, or where production reduces by 10%. So we can also reduce production by 10% or doing so in the model. Or in the case where we're adding a submersible pump, we can initiate that within the model. Other questions that we have here, and I know we have time maybe for 2 more questions. One of them is, do you have any material related to gathering system analysis? Actually, yes. Well, it's not really material, but I know that we have a presentation on how to quickly identify existing bottlenecks, as well as providing an interface to run optimization or decommissioning scenarios. So if you're interested in this, please just send me an email, and I'm happy to follow up with you on this material that we have. Another one is, do we have documentation on how close the results can come when using this methodology? Yes, we do have a couple of companies that have evaluated our software, and they were able to get forecasted results and field results as close as, I think it was 3.5%, and we actually documented that in a paper. I can actually send you the details of this paper to you, and also information on how close our results actually come as well. Also, I think before we run out of time, I just want to obviously thank you for your time during this presentation. I hope that it has been of great interest, and here there are a couple of links if you want to follow up in any of our software or any of the material that we have. And I will follow up with any other questions that you guys might have on this presentation. Have a nice day. Thank you.